Hello, everyone. In the last lecture, we started chapter 3 of the Domingo's book. And in that lecture, I covered several topics up to independence. Right? That means I discussed about joint and marginal CDF, joint and marginal PDMF, joint and marginal PDF, an expected value, and then independence of two random variables. In today's lecture, I'm going to continue from there. First, I will look at some examples which use the stuff that we have discussed so far. And then we will also look at a new topic called conditional distribution. So as usual, this lecture will be broken into 2 or 3 videos, uh, totaling about 3 hours. Right. So let's start with the examples. This example is taken from Demidenko's book. This is problem 21 in the chapter 3. This is an interesting problem, kind of practical problem also, but simplified version, of course. An oil spill happened in the ocean. Due to wind, the oil spill moves towards the shore, making 1 feet per second in the x direction and 2 feet per second in the y direction, independently, with probability 2/3 and 4/5 respectively. So we are considering some origin. We consider the origin as the point where the spill happened. How many hours it will take before the oil spill reaches the shoreline specified by the equation x plus y is equal to 52,800 with probability 0.9. Make and state necessary assumptions. So we are going to assume that the place where the spill occurred at the origin, and then from that point, we are considering a coordinate axis, coordinate system with x and y. So this is considered as a two-dimensional problem. So it says that the oil spill moves in x direction with 1 feet per second with probability 2/3. That means the probability that the oil spill moves in the x direction 1 feet, right? Either 1 feet with probability 2/3 or 0 feet with probability 1/3. So this is a very simplified version. There are only 2 possibilities. Either it is moving 1 feet per second in the x direction or 0 feet per second. And similarly, in the y direction, it moves 2 feet per second with probability 4/5 or 0 with probability 1/5. So that's the condition. So the problem is how many hours it will take before the oil spill reaches the shoreline specified by the equation x plus y is equal to this value with probability 0.9. Right. So what are we looking at here? We are looking at a certain probability of that after some time, after say n hours, for example, uh, the position, the coordinates satisfy x plus y equal to 52,800 with probability 0.09. So every hour, X values and Y values are added up. So we are going to assume that this number of hours for this to happen will be a large number, because here there's no other way actually, because we'll have to look at the sum of some random variables. Uh, and some information is given, and from that also we can reduce the distributions from the from for the movement in x direction and y direction. So let's look at the problem. Let's formulate the problem in mathematical terms. Assume that at each second, right here, yeah, the question says uh, it's moving 1 feet or 2 feet per second. So we are going to consider what happens in every second. Assume that each second the oil spill moves xi feet in the x direction and yi feet in the y direction uh, in the ith. Right. So each second that happens, but in the ith second, we are going to assume that the amount that it moved in its direction is xi, and the amount that it moved in the y direction is yi. So these are random variables. So according to the given information, xi is equal to 1 with probability 2 over 3 and 0 with probability 1 over 3. There are only two possibilities for xi. And for yi, similarly, yi will be either 2 feet, with that is with probability 4 over 5, or 0 with probability 1 over 5. Right. So here we can easily see that xi takes values of 1 and 0 only. So that's therefore, according to the usual definitions, that's called a Bernoulli distribution. Bernoulli distribution with probability 2 or 3 of success. But yi takes values 2 and 0, therefore it is not a conventional Bernoulli random variable, but it's a discrete random variable with two possible values given by these with these properties. Right. So what we are going to look at is what will be the position after n seconds, say for example, n seconds, where n assumed to be large number, n seconds. So therefore, for the first second, there will be a x1 and y1. For the second, there will be x2, y2, and so on. So therefore, after n seconds, the oil spill's position will be given by sum of xi, I from 1 to n, plus sum of yi, uh, because that is the quantity we are looking at, the x coordinate value plus y coordinate value. So x coordinate value will be sum of xi's, I from 1 to n. Y coordinate will be sum of yi's, I from 1 to n. And what we are interested in, the sum of those two, right? So this is the quantity that we are looking at, Sn say. So that will be I from 1 to n x summation xi plus y, right? So the shoreline is reached if Sn is equal to this number. So what we are interested in is that actually what is the probability that Sn will be greater than or equal to this number with point 0.09, right? So it's reaching means the total Sn will be greater than or equal to, so reach or even pass, right? At least reach, right? So the question is, what is this n should be, right, for this statement to satisfy? So we are going to assume that n is large, and thereby we are going to use the central limit theorem to get the distribution of Sn, because without knowing the distribution of Sn, it's difficult to find out uh, you find out n, right? Because we have to solve some expression in n to solve this. In order to get that expression, we need to know, we need to at least assume some distribution. So we have to assume a reasonable distribution for Sn. So we will use the central limit theorem to find the approximate distribution of Sn, and thereby we will find out n satisfying this equation here. So what does central limit theorem say? If, for example, here this is, you can consider this as, for example, Zi, say xi plus yi is equal to Zi. So each Zi is independent and identically distributed, right? Because xi and yi are independent. Uh, So x1 and x2 and x3 and so on are independent. Y1, Y2, Y3 and are also independent. And also x1, Y1, x2, Y2, they are also independent. So what we will have is a summation of IID random variables. Right? Each Zi term will have the same mean, each and variance. So, according to the central limit theorem, in that kind of situations, if n is large, then Sn should have approximately a normal distribution with mean equal to the theoretical mean of this quantity, plus variance will equal to the theoretical variance of this quantity. So, therefore, in order to find out the distribution, now we know it should be approximately normal. But in order to get the required expression, we need the expected value and the variance also, right? So let's therefore look at uh, get the expected value and the variance. So what you need is expected value of Sn, that will be equal to I from 1 to an expected value of xi plus expected value of yi. Variance of Sn will be equal to, again, I summation I from 1 to n variance of xi plus variance of yi. You can write down like that because xi and yi are independent. Otherwise, there will be some covariance term coming in. But in this case, because xi and yi are independent, covariance becomes 0. Right. Uh, so now we know that each xi has a certain Bernoulli distribution. So we can therefore use the theory that we know about the Bernoulli, that we know that expected value has a certain form, and we know the formula for the expected value. When you know the probability of success, we know the variance. So you can directly apply that. But in order to find out the mean and the variance of yi, we cannot use that theory because yi doesn't have a Bernoulli distribution. So therefore, we will just find out that using the uh, uh, definitions of expected value and variance of the random variables. Okay, so as I mentioned, then expected value of Sn will be equal to expected value of the sum of xi. So that will be the sum of expected value of xi, like that, and similarly this one. But here actually we can get it instead of considering expected value of xi, even that is also okay. So we can get it using the Bernoulli distribution properties, and here we'll have to calculate uh, uh, in order to get this one, we will need to calculate it using the definition. Right. So we know that sum of xi, because each xi is Bernoulli distribution, has a Bernoulli distribution with me probability of success 2 over 3. Sum of xi has a binomial distribution with number of trials equal to n, and the probability of success equal to 2 over 3. Therefore, we know that expected value of a Bernoulli random variable with n and theta is equal to n times theta. So therefore, expected value of this quantity will be n times this one, and variance will be n times theta times 1 minus theta. So therefore, it's going to be this expression, n times theta times 1 minus theta. On the other hand, in order to find out the expected value of yi, we know that it's going to be just yi can take only two values, right? So therefore, expected value of yi will be this number times this probability plus this number times this probability. So it's going to be 2 times 4 over 5. So that is the expected value. In order to get the variance, we need the expected value of yi square. So that's again going to be 2 to the power 2 times the corresponding probability. So it's going to be 4 times 4, 5. So using these two, we can get the variance of yi. Variance of yi is equal to expected value of yi square minus the square of the expected value. So we get this answer from that. So therefore, we know expected value of yi and also variance of yi. Therefore, the expected value of sum of yi terms, n terms will be n times this quantity. Variance of the sum of yi values will be n times this quantity. So therefore, the expected value of sum of yi is the variance of sum of yi. So therefore, the whole thing we can get the expected value of Sn is equal to the sum of the two expected values. Variance of Sn is equal to sum of the two variances, and you get this expression. You can see that these quantities contain n, right? So now we are going to use the central limit theorem. N is large, therefore Sn should be approximately normal with this mean here, this variance, right? So that's coming from the central limit theorem. So therefore we can look at now, it is the required condition. We have to solve n satisfying this condition, right? So therefore, in the usual way, we can standardize. We can write down this probability in terms of the standardized variables. So take away the mean and divide by the standard deviation. So this becomes a standard normal random variable now. So on the right hand side, you have a number, and that number should be equal to the upper 90th percentile of a standard normal random variable. So this quantity should be equal to the upper 90th percentile or upper 10 percentile, right? From the right hand side, but from the left, if you consider the whole probability. Oh no, this is greater than or equal to. So this actually, sorry, this is this thing greater than or equal to zero. So this value should be actually the 10th percentile low on the left, because the area above that has to be 0.9, right? We are considering this is said greater than or equal to, this should be equal to 0.9. So therefore this number should be the 10th percentile, right? So of the standard normal distribution. So the 10th percentile is this number, negative value, of course, because it said uh, is symmetric around zero. So the 10th percentile in the left hand side. So this is a negative value. So when you solve this, you can get the expression for n in seconds. So this is the answer I get. N is equal to this number approximately in seconds. So you can convert it into hours by dividing by 3,600. It's approximately 6.45 hours. So therefore, we can say, according to this simplified model, the oil spill reaches the shoreline with probability 0.9 after it started approximately in about 6.4 hours. That is about 6 hours and 27 minutes approximately. Of course, as I mentioned, this is a very simplified model, but in this case, we were using uh, two random variables. Of course, the random variables were independent in this case. Therefore, we were not directly looking at joint distributions or anything here. So this is a very elementary type level problem, but still two variables are involved. Right. Now we will look at a little bit more realistic situation, but still it is a simplified version. In the previous problem, each second the oil spill moves either 1 feet or 0 feet in the x direction, and either 2 feet or 0 feet in the y direction. Right. So that's a very strong assumption. Actually, the amount that it moves in a second, in a given second, can be some other random variable, like the amount may be given by some, according to some other distribution. Here in this problem, we are considering that kind of situation. But still the problem is a little bit simplified. We are considering only two possibilities. Either it moves certain amount or doesn't move at all, right? Uh, with some positive probabilities for both cases. An oil spill happened in the ocean. Gusty winds and rough sea moves the oil spill towards the shore. The distance covered in the x and y directions, in this case, the values are given in meters per hour, is also coming from the same book, but it's a different problem. Example 3.54. So the movements are in meters per hour, and it says that the movements are exponential. In the x direction, the movements are exponentially distributed with rate equal to 1 over 150. That means mean movement is 150 meters per hour. And the other one in the y direction, lambda is equal to 100. That means the mean movement is 100 meters per hour, with probability 3 over 5 and 1 over 2 respectively. So a certain exponentially random distributed random variable amount will be the movement in the x direction. The probability of happening that is 3 over 5. Otherwise, the movement is 0 with probability 2 over 5. In the y direction, the movement is again exponentially distributed. Uh, uh, that will happen with probability 1 over 2, or it will be not moving at all with probability 1 over 2. Right. So approximate the probability that the oil spill does not reach the shoreline given by the equation x plus y is equal to 3000 using the central limit theorem. Right. So it's a different question. Earlier we found out the probability that it reaches the shore. Now we have to find out probability does not reach the shoreline given by this thing. Right. Does not reach. Estimate the probability using actually this there. I think there's some missing part here because it says does not reach in how many hours. It's not very clear here. Estimate the probability using vectorized simulation. So we have to calculate the same probability, first of all, theoretically, and then using simulations, and also display the oil concentration on the shore, again, using some graphical method. Right. So we will go similar to the previous one, except now the values, movements are exponentially distributed, right? Either exponential distributed amount or zero. Right? In the ith hour, the spill moves xi meters to the right with probability 3 over 5, where xi follows an exponential distribution with rate 1 over 150. Similarly, it moves yi meters, we will consider that later, to the y direction with probability half, where yi follows an exponential distribution with rate 1 over 100. So that's the question. Those are the information that we have. So after n hours, the x coordinate will be sum of I from 1 to n uixi. So this is a new method of writing down that we write down this and we denote it by dnx, distance in the x direction after n hours, right? You can use whatever the notation you like, but here I'm using dnx, right? Because it depends on n and it's in the x direction. It's a distance, so therefore I denote it by dnx. And we can write down that thing as sum of ui times xi, where this ui will be either 1 or 0. Ui will be equal to 1 with probability 3 over 5. Ui will be equal to 0 with probability 2 over 5. Right? So therefore, in the uh, ith hour, the distance it moves will be equal to 1 times xi or 0 times xi, where xi will be an exponentially distributed random number, right? So where ui is a Bernoulli random variable in this case, because ui takes value 1 or 0. So So therefore, directly we can get, because we will need the expected value of ui, we will need the expected value of this quantity. And this ui and xi are independent, right? ui and xi are independent. So when you are calculating the expected value of dnx will be equal to the expected value of sum of this product. That will be equal to sum of the expected value of this product. But in the last class, we saw that if x and y are two random variables are independent, then the expected value of the product will be equal to the product of the expected value. So we can write down, then you can use that expected value of this product is equal to expected value of ui times expected value of xi. So therefore, we need expected value of ui. We can directly get it from this information. So that is actually expected value for ui will be equal to 3 over 5. It's equal to theta. Variance of ui will be equal to 3 over 5 times 2 over 5. And also we need the expected value and the variance of xi also. Expected value of xi will be equal to 150. Variance of xi will be equal to 150 square. So those are coming from general, well-known results about the exponential distribution, right? So as I mentioned, you can write down these things. The expected value of ui is equal to this one. Variance of ui is equal to this quantity, right? Expected value of xi is equal to this one. Variance of equal to this one. And I have calculated the expected value of xi square also, because we will need it that later. So therefore, I have calculated that also. Expected value of xi square and also expected value of ui square, right? Expected value of ui square we can easily get because it is just one square times the corresponding probability. So you are going to get the same value as expected value of ui. But expected value of x square, in order to get that one, you have to use this formula. That's equal to variance of xi plus uh, the square of expected value of xi. This is the short notation for the square of the expected value of xi, right? That whole square of the whole thing, expected value of xi. So your answer is this one. And similarly, for the y direction, we denote the total movement by dny, and similarly we can get the corresponding values, expected value of vi. Now here earlier I used u, now I am using v here because we need a different random variable, but vi also can take value 1 or 0. So vi is also Bernoulli random variable with probability of success equal to half and probability of failure is equal to half. So therefore, using the same methodology earlier, we can find out expected value of VI, variance of VI, expected value of VI square, and similarly, expected value of YI, variance of YI, and so on. Well, so these are here. Now, XI and YI are independent, UI and VI are independent. So therefore, UI xi is independent of vi, yi, right? So therefore, this whole dnx is independent of dnx term is independent of dny term, right? So what we need is the probability that probability does not move in n hours, right? So the question, in order to simplify this, we have to find out approximate probability that the oil spill does not reach the shoreline given by this thing in a given n hours. So we are going to get the expression for some n hours, and then we can, of course, if you want to look at a particular n hours, then you can have to substitute that n and simplify it and get the answer. Generally, we are going to get the answer in terms of n here, right? So therefore, this is the quantity that we are interested in, and we want the probability of happening this. Right? This is the x coordinate after n hours. This is the y coordinate, and the shoreline is x plus y is equal to 3. does not reach the shoreline means x plus y less than 3000. Right. So again, we are going to use the central limit theorem. Dnx will have approximately a normal distribution if n is large with mean equal to this thing and variance equal to dnx. We have already got the answers. Uh, no, we have got the individual values, but now we can get the corresponding values. Expected value of dnx is equal to n times expected value of ui xi for any I, because these all ui xi terms are IID, independent and identically distributed. Now, because ui and xi are independent, expected value of ui times xi is equal to expected value of expected value of ui times expected value of xi. And then you get this as the expected value. And similarly, variance is equal to, this is where you need the squared terms of the expected values, right? There is no other way to get, for us to get the variance of this product. So we have to use the usual definition, right? So this consider, for example, this as from one random variable. We know that variance of a random variable is equal to expected value of the square of that random variable minus the whole uh, square of the whole expected value, right? Square of the expected value. Here, expected value of the squared random variable minus square of the expected value of the random variable. Right. So, because u and xi are independent, any function of those also are independent. Therefore, you can write down this one as expected value of ui square times expected value of xi square. And this one, of course, will be expected value of ui times expected value of xi, then whole thing square. Right. So you can substitute the quantities that we have already found, and therefore finally you get the variance equal to this expression. So we know that expected value of nx and the variance of nx, variance of dnx, sorry, and expected value of dnx. And similarly, we can find out expected value of dny and the variance of dny exactly the same way. So now what we need is actually dnx plus dny, right? So therefore, they are independent. Therefore, their expected values and the variance will be just the sum of the expected values and the sum of the variances. So therefore, finally, dnx plus dny will have approximately this distribution normal, right? Assuming n is large. So therefore, what we need is this expression, the probability dnx plus dny to be less than 3000. So again, doing the usual standardization, we can show that this is equal to the cumulative standard normal probability evaluated at is 3000 minus the mean divided by standard deviation. Right? So that value, pi. So that is the expression that we can get actually in terms of n, right? And we cannot simplify more than that unless we substitute a value for n, right? So if we, for example, are interested in what is the probability that the oil spill will not reach the shore within a day, then we'll have to substitute n equal to 24, right? So this is generally a function of n, but for any fixed value for n, we can calculate it. So in that case, we'll have this d24x, 24y, and less than. So it's, when you substitute here for n equal to 24, you can get this using r simply, very simply, that is going to be 0.326. So therefore, there's the approximately 30% a chance that the oil spill will not come to shore within 1 hour. That means approximately 70% chance that it will come to the shore within 1 day. Sorry, not 1 hour, with 1 day. Right. Okay, so that is the answer to the first part. And then it asks us to get the same answer, not the same answer, but get the answer using simulations. Right. So this is what we can do. I'm going to look at about 10,000 simulations. Right. So I will consider 24 hours. That means sum of xi and sum of yi terms 24 times. And then look at whether dnx plus dny less than 3000, no greater than 3000. If it is less than 3000, then it has not reached, right? Otherwise, it has reached. So like that, do again another situation, consider it again the same thing. And then in that case also look at D24X and D24Y, whether that is less than 3000 or not. And thereby we can see whether the spill has reached or not. So like that, when you do 10,000 times, in some 24-hour time periods, right, that we consider, simulate, dnx plus dny will be less than 3000. In some, the others, it will be greater than. So we can find out the probability that the dnx plus dny less than 3000 by looking at the number of times dnx plus dny less than 3000 divided by 10,000, right? So what we have done is here, I have considered 10,000. So I will directly at the same time, not to one by one, because here what we are doing is we are calculating dnx and dny. Dnx is equal to u times x, and the other one is v times y, and so on. So we will just consider some random numbers, 10,000 random numbers, and then directly take the necessary quantities. So as I'm going to consider NSIM is 10,000 times 24 random numbers from binomial distribution with n equal to 1. So I want Bernoulli, right? So therefore it's a binomial with n equal to 1, probability equal to 3 over 5. So I'm going to put it in a matrix. That means each matrix will have uh, 10,000 values, 10,000 rows, and this matrix will have 24 columns. So one column is considered as uh, uh, one row is actually a day, right? Another possible, what can happen in a given day. So the second row is another thing, what can happen in the second row, and so right. So UI values for the day, right? Or that means for that simulation, particular simulation. So there will be uh, n row is equal to number of simulations, n call is equal to n. And similarly, I need another random numbers v, again binomial Bernoulli with probability half. So similarly that. And then X numbers are the exponential random numbers. Again, the same idea. I will have 10,000 rows, but each row will contain 24 numbers. My X values are coming from exponential with rate 150. Y values are coming from exponential rate with rate 1 over 100. Right. So dnx will be equal to then I can just multiply these uh, column by column. It's not a matrix multiplication, right? Corresponding column. First column of u multiplied by first column of x. Second column of u multiplied by second column of x, like that, right? So column wise multiplication will be given by u times x, and then for each I want to add 20 some take the rows, some of the u I x I terms, I from 1 to 24, right? So for that I get row sums. So therefore I will get finally row sums u times x will have uh, 10,000 values, and similarly row sums v times y will have uh, 10,000 values, right? So the first value in this number is the position or the location of the point, actually x coordinate of the oil spill after 24 hours. And the first number in this column will be the y coordinate of the oil spill after 24 hours. So therefore I can get x plus y for that particular 24-hour period, right? Similarly, I want to get x plus y, dnx plus dny values for all these 10,000 possibilities. So that's why I say dn, I call it dn is equal to dnx plus dny. So there are then 10,000 values. Out of those, I want to find out how many values are less than 3,000, right? So I want the probability. So either I can look at the sum of this condition, dn less than 3,000, that will give me the number of times dn less than 3,000. Then in order to get the probability, I'll have to divide it by 10,000. Or directly I can get the probability by calculating the mean of dn values which are less than 3,000, right? So actually what happens is not the mean of dn values. What happens is this condition will be true or false values. So when you calculate the mean of that true false column, I will get uh, the proportion of times the true occurs, right? So therefore, that will be the probability. So when I run it, I got answer 0.3401, whereas the theoretical value was this number 0.326. Right. So you can see that it's 3, 4, and 3 here 3, 3 up to two decimal places. So it's pretty close. If I run it again 1,000 times, it will be something else. But if I increase my NSIM, answers will be more close to the actual probability. Here I'm presenting only 10,000. Right. So that's a simple program using the vectorized uh, values, right? So you don't have to run a for loop here, right? You can do all these 10,000 simulations just very easily using vectors, right? Um, Based on the simulation, the probability that the oil spill does not reach the shoreline in 24 hours is 0.3401. And then it asks us to draw a graph showing the situation. So I have written down a small program again. Actually, what I looked at is the same thing, but uh, here I have 10,000 possibilities. So if I draw those 10,000 possibilities in the same graph, it will be very difficult to see any different any we cannot differentiate the paths, right? What I'm going to do is the possible paths, right? Some of the paths may reach the shoreline, some of the paths may not reach the shoreline in 24 hours, but I don't want to draw all 10,000 paths. Therefore I'm going to consider only 100 of those possible paths, right? So I consider A to be U times X, where U and X were the same things that I generated earlier, but only the first 100 values. Uh, and then, so this is actually the matrix, right? First row, 100 rows and all the 24 columns, right? So this U times X will give you a matrix, right? Because it's multiplying column by column, right? uh, column wise. First column and second, first column in U and first column in X, second column in U and second column in X. Because this is the usual multiplication sign here. Otherwise, if you use the matrix multiplication, you get a different answer. That's not what we want. Right? So from that, we will take the first 100 rows. And similarly, I call V times Y plus 100 rows. Right. So now I want to look at the cumulative sum, right? Because I want to get the whole path. What these conditions, these contents are the movements in each hour separately. So in order to get the path, I'll have to add the first movement and then add to it to the second movement and so on. Therefore, I'll have to look at cumulative sum. So I use this apply function for A, right? And then in rows, I am going to apply it. And then I will call it SX, right? Uh, that will be the sum of those movements in the X direction, right? I'm going to, now here you are going to get a column, but I'm going to put it as a row. Therefore, I put T to get the transpose. And similarly, SY will be the locations after each hour, right? By applying again cumulative sum. And then S will be the sum of those two, Sx plus Sy. Right. So now I want to find out which of those values are actually, because I want to create a picture with two different colors, right? I want to show those paths that did not reach the show by one color, and those paths that reached or even moved far further than this thing by some other color. Therefore, I'm going to create some variable uh, for those dummy, variable with two possibilities, so that I will be able to use that as my color indicator, right? So I first of all say G is equal to just one, 100 ones, but then what I do is I say I want to have color 1 and color 4, right? So for those distances, these distances here, where D's will be less than 3000, I want to have the value G as 4, because 4 is representing a certain color. I think it's blue, right? So therefore, if D less than 3000, now my G value will be 4, otherwise G value will be 1, right? So I have two numbers in this vector of 100 numbers, right? So now I want to plot this Tx and Ty, Tx x coordinates in the sum, cumulative sum coordinates, and cumulative sum coordinates in the y direction. I want to plot as a matplot. So x values will be given by this, y values will be given by this. Notice that these are here I have got the transposes. Now I want to get again the column. Therefore, I look at T of Sx. Actually, this point was not necessary. If I wanted, uh, I could have omitted this part. But but I think the problem is, yeah. I think the problem is that in order to get the cum sum, you have to have it in this form. That is the problem, right? So when I use this command, and then I show the shoreline also with the uh, x plus y is equal to 3000. So that is y is equal to 3000 minus x. So that is the same as straight line with intercept equal to 3000 and slope equal to negative 1. You can get that line by using AB line command. Here A is the intercept, B the slope. And this is the line width I'm specifying a little bit dark, a thick line, and the color, so asking for the red color. Color is 2. Right. So when I do that, this is the graph that I got. So you can see that there are some parts in blue, that is color 4. Those are the parts that did not reach this red line in 24 hours. So the end of these are not touching this red line. All the others out of this 100, there are all 100 parts here. All the other hundreds lines, the paths in the black, are actually either touching this thing or moving past that. Right. So red line is the show, blue paths did not reach the show. Right. So those are two interesting examples. So I think this is a good place for me to stop this part of this lecture. In the next part, I will look at another example. Actually, it's kind of a theory taken again from the book. I will define something called convolution, and then look at few examples using convolution also. Right. So therefore, I'll stop this video here.